Welcome to Chapter 4, Geometry. We are talking about triangle congruence. And this warm-up is a little bit of a stretch, I think, but see what you can determine, and then after the lesson, you might be able to look back and understand the warm-up question better. It's funny how they did that in this case. So try it and see, come on back and see what you got. All right, so hopefully when you graphed this, you saw that this was simply a slide, right? It was a translation 6 units to the right. Okay, so we were adding only to the x values, 6 units in each case. And this one down here, notice that the numbers look close. However, the y values are all negative. So we have a reflection, right? Reflection across the x-axis when we have opposite y's. So you have seen a little bit of that before, and now you're ready to really dive into a lot of transformations involving congruence, and in some cases, transforming things into larger or smaller images too. So the objectives are to draw, identify, and describe transformations in the coordinate plane. We will use properties of rigid motions to determine whether figures are congruent, and also to prove that figures are congruent. So something with a scale factor that is greater than 0. What do we call something when, if we start with point x, y, and then we multiply each coordinate by a factor greater than 0, what happens? We get what we call a dilation. Okay? A dilation of factor k. Okay, so here we have a point that's been dilated. It feels like a stretch from our algebra lessons. When we're talking about transformations and we are looking at them on a coordinate plane, the original figure is known as the, interestingly enough, it's known as the pre-image. Okay, the pre-image. And then the resulting figure after the transformation is called the image. So imagine you take a picture, you now have an image of somebody. The actual person would be coming before the image, right? The pre-image. So pre-image is the original, an image is the transformed figure. Okay, we're going to apply transformations and describe them. So jot down a quick coordinate plane and graph point P, Q, and R, and then you're going to find the image by applying these rules to each x and y. And then you'll graph it. Okay, so let's look at this together. Okay, so jot a little coordinate plane and plot your little triangle, PQR. Now if we're going to apply this transformation, each coordinate now is going to change, right? So let's jot down the coordinates of our new transformed figure. Okay, so we could say that P prime, let's see, the original P is at 1, 3. So x value of 1 now becomes 1 minus 4, which is negative 3, right? And the y value of 3 becomes 3 plus 1, which is 4. Okay, so there's our P prime. Q prime, and I know you can see this better on your paper, right? Let me stretch this. So the original Q was 1, 1, right? And so now we're going to apply this transformation. So to the x, we're going to substitute this x in. 1 minus 4 is negative 3. And we have 1 plus 1 now, which is 2. And finally we have r prime, our image of the point r. Plug in your x and you get 0. And plug in your y value of 1 plus 1 and you get 2. Let me stretch this a little further. Let it come back up. There we go. Okay, so here we have the coordinates after having applied the rule. And when you go and plot these, go ahead and pause and do that, you get a triangle that has gone the left 4, and up 1. What type of transformation do we call this? That's right, a translation, 4 units left and 1 unit up. All right, so let's try a second transformation. Pause the video and find the coordinates of our new figure, the image, given this pre-image. Okay, make sure you pause and apply that rule. And once you have, A prime becomes 1, -2, right? B prime becomes 4, -2. And C prime becomes 3, -1. Okay, so you now have the math behind these coordinates, and then go ahead and plot them. And what do you get? You should have an image that looks like this red figure, right? So what is this transformation? We're hopping over this axis, aren't we? So we call this a reflection in the x-axis, or a reflection across the x-axis. Okay, you've had a couple of opportunities in the past to perform these transformations, but we're going to try one that you haven't tried, probably. Look at what happens here. xy transforms to y is now in the place of x. Look at that. You switch the locations, and you take the opposite of x. So go ahead and pause the video and perform this math, and then we'll come back and go ahead and use this graph to graph what you have, and we'll check it out. Okay, make sure that you've tried it yourself before you check your work. In R prime, now we're going to switch these two, x and y, to the opposite locations, and then we're going to take the opposite of x, right? So 0 comes here, and we take the opposite of -3 in the y position. Okay, same is true here. We're going to bring the 3 to the x position, and now take the opposite of -3, and so on. Good. So take a moment to plot. You can use this if you like. And if you're back, let's see what this looks like. The original figure is in blue, and the image transformed in red. Isn't that fun? So what happened here? We call this a 90-degree rotation clockwise, with a center of rotation being at 0, 0. And there you go. Isn't that cool? Very fun rotation transformation. So we're rotating 90 degrees about this point, taking this point 90 degrees, like from 9 o'clock to 12 o'clock, right? We're taking C prime from what looks like pointing up toward 12 o'clock on a clock to pointing toward 3 o'clock. See that? Taking R, which looks like it would be pointing, what, I guess it depends on how you look at it, huh? But let's say it's pointing, T to R is definitely pointing toward 9 o'clock, right? And now T prime to R prime is pointing straight up to 12 o'clock. So it's a 90-degree rotation. Very cool. Okay, what happens when we multiply each of the coordinates by a factor? In this case, the same factor. Go ahead and find the values and graph. Okay, so you should have K prime at -6, -3. L prime at 3, -3. And N prime at 3, -6. And your graph looks like this. Here's a little pre-image, and here is our transformed image. And notice what it has done. It's gotten larger, hasn't it? It feels like it's been stretched, and we call this dilation with a scale factor of 3, given the center at 0, 0. Very awesome. Okay, we're going to skip that additional sample. We just saw the same kind of transformation. So let's jump straight to our summary box here that explains the various transformations we've been talking about. Okay, so this type of transformation, where we go from an original to an image by adding to the x and y, is called a, that's right, translation. Okay, that moves our figure A units left and right horizontally, and B units vertically. Okay, what type of a transformation takes the original coordinates and just takes the opposite of the x or the opposite of the y? We are reflecting, right? Reflecting, in this case, you're reflecting in the y-axis, and in this case, we're reflecting in the x-axis. Okay. Could we reflect in both axes? Sure, we could just take xy to negative x, negative y. We could reflect across both. So, kind of fun. This case, we have an original going to, we're switching the locations, look at that, of the x and y. xy becomes y negative x. xy becomes negative yx. So these are rotations, right? Rotations. We just saw this one. This was a 90-degree clockwise. In this case, the y is negative, so it's a 90-degree, possibly counterclockwise. Let's check that out in our work today, right? And then what happens if we make both of our values negative? We have a rotation about 0, 0 of 180 degrees. I was just referencing that here. You end up with an absolute 180 degree rotation. Okay? And then finally, we just saw this in our last sample. When we multiply each coordinate by a factor that is greater than 0, look at that, we're multiplying by greater than 0, we have a dilation, a larger figure, right? Whoops, let me undo that. Let me just take this off. There we go. So we have a dilation with a scale factor of k. A transformation that preserves length, angle measure, and area is called an isometry. Iso meaning the same. So we have a transformation that might be a translation where we still have a congruent figure, it's just moved on the coordinate plane. It could be a reflection as well, right? Or a rotation. Okay? So a rigid transformation, rigid is another name for isometry, right? Moving something rigidly means keeping its congruent size and shape, just simply moving it around somewhere else on the coordinate plane. So translations, reflections, and rotations, as I just said, these types of transformations produce images that are congruent to their pre-images. But dilations, like we saw when we multiplied x and y by 3, change the figure from an original to something that's larger, right? So these produce images that are not congruent to their pre-images. Of course, if you multiply by a factor of 1, you wouldn't be changing an image, right? So this is true. Dilations are true when we have a factor that is not 1, right? Okay, so in this case, we are being asked to determine whether the polygons are congruent. So we want to know if the transformation here, going from ABC to PQR, if that transformation is a rigid transformation, right? An isometry, which would mean a translation, a reflection, or a rotation. So knowing the rules that we just described, can you see a relationship between point A and P that applies one of those rules? And then test it with B and Q and R and C and R, right? And jot down the transformation. Okay, so we do see that 2, -1 becomes 1, 2. Look at the coordinate pair has switched locations, and the 1, the y here, became opposite, right? So this is a rotation, isn't it? Let's test it here. Did the 3 and 0 switch places? 0, 3, yes. And the y, 0, became, it can't become opposite, it's neutral. So let's try C. 2, 3, did it become -3, 2? Yes. So we could write this as xy transforms to -yx. Yes, the triangles are congruent because a rotation is a rigid transformation, an isometry. Oops. Okay, how about here? Prove these polygons with the vertices are congruent. So here we have them already plotted for you. So what is the transformation that allows the blue triangle to become the red triangle? Can you figure out the math behind that? Pause the video and try it and come on back. All right, this one's really a little bit tricky, but if we translate this blue figure first, okay, by subtracting 3 in the x and adding 1 in the y, so translate the entire figure over and up here, and then we rotate the figure using this rotation transformation, we end up with the red image. So because we can translate and rotate, we have a isometry, don't we? We have a rigid transformation. Okay, this is interesting. We're proving that ABC is congruent to PQR, and we're doing that by, you can go graph if you like, but what's going on here is a translation, right? We're adding 5 to the x and 2 to the y values, and then we're reflecting that across the x-axis by taking the opposite y. You don't really see that as clearly with P and R, but you see that clearly with going from B to Q. The negative of 0 is still 0, so that's why you don't see it with P and R. Okay? Okay, there's yet another name for these types of transformations, the type that keep a figure the same congruent shape. So we have rigid, we have isometries, and we can also call them congruence transformations. So in case you run out of synonyms, here's another for you. All right, we're going to skip straight over to the lesson quiz and give it a try. Come back and check your work. The answer to number 1 is dilation, scale factor 3. Number 2, 90-degree rotation. Try part 2, come back and check your work. And the answer to number 3, translation. And to number 4, we have not a congruent transformation. So we actually have a dilation by a factor of 2. In proving that these two are congruent, that would be triangle ABC and then triangle DEF. Pause and think about it. How do we know? A translation and then a reflection. Okay, day 1 is the first day. We'll come back and talk about these things and then work on day 2. Have fun!